All right, day 2 of continuous probability distributions. Today we're going to look at some applications of the normal distribution, and we're really going to be delving into what statistics looks like at a post-secondary level today. So that's kind of exciting. So remember yesterday the the normal distribution that we were using with our continuous variables. It has this nice bell shape, high in the middle, symmetrical, tapers off to both sides. Some properties of this are clearly the highest point, the point with the highest probability, is in the middle, and that center value is the mean and the median. They're the same place in this distribution, so that's always nice. And then we have some really cool properties of the normal distribution. We could look at these. We'll look at these ourselves where they come from in a second, but we'll observe that if you are between one standard deviation below and one standard deviation above the mean, well, that's over 2/3 of all possible values. 68% will be the value we'll be using here. There's a few more decimal points, but good enough for us. So that would be a z value of -1 and a z value of 1. If we look at the center one, if we go out within 2 standard deviations above and below, so a z value of -2 and a z value of 2, well, that contains 95% of all the probability. So you remember a while ago we were looking for outliers. A value of 1.5 to 2 standard deviations for outliers makes a lot of sense, because only 5%, only the rarest values, are outside of 2 standard deviations from the mean. And sometimes we care about being even more precise, so within 3 standard deviations above or below, a z value of -3 or a z value of 3, that contains 99.7% of all the possible values. And knowing this can be really, really handy for some shortcuts. But first, let's look at confirming this information to ourselves. Hopefully we're always a little skeptical until we see evidence of something. So the birth mass of a breed of guinea pigs follows a normal distribution, and that's kind of key to everything that we're doing right now, right, is that it follows a normal distribution. So that means we can apply everything that we've been talking about. With a mean of 100 grams and a standard deviation of 10 grams. So what's the probability that, the birth mass, I think that's an autocorrect error. Whoops, we'll fix that for next time. What's the probability that the birth mass lies within 1 standard deviation of the mean? So from above, we know it should be 0.68, 68%. But let us check that out for ourselves. So within 1 standard deviation means 10 above, 10 below. So we're looking at the probability that 90 is less than or equal to x is less than or equal to 110, which from last day is the probability that x is less than or equal to 110, whoops, grams minus the probability that x is less than or equal to 90 grams. So we'll do our calculations. We would normally take our x and calculate our z value, but in this case we know we're 1 standard deviation away and we're below, so the z value for that is simply -1, and for x is equal to 110. That's 1 standard deviation above, so z would be equal to 1. So we'll look that up on our z table. If you need a second to look it up, you can pause the video, and we will get 0.8413 for 110 for a z value of 1, and for a z value of -1 we will get 0.1587, giving us a total probability of 0.6826. or 68.26%. Just like we knew from above, but now we see where it comes from and that it actually works. So let's double check for 2 standard deviations from the mean instead. So in this case, that would be the probability that 80 is less than equal to x is less than equal to 120, which is the probability that x is less than or equal to 120 minus the probability that x is less than or equal to 80. And in this case, our z value when x is equal to 120, z is equal to -2, and when x is equal, going too fast. When x is 80, z is equal to -2, and when x is 120, well, z will be equal to 2. So when z is 2, our value is 0.9772, and for a z value of -2, we get 0.0228, giving us a total probability of 0.9544, or 95.44%. So for today, we're showing how we did it. In the future, I'm totally okay with you just referring to those values for a question. You don't need to calculate if it's something about precise 1, 2, or 3 standard deviations. Recognizing that 1 means 68%, 2 means 95%, and 3 means 99.7%. All right, so moving on. So in real statistics, we understand that everything is based around probability. There's always uncertainty. When we take a sample, our sample is not going to perfectly represent the population. Sometimes you get a good sample and you get a very good representation of the actual population. And sometimes you get a bad sample that can actually be deceptive and unlikely. So since we don't know exactly whether we've got a good sample or a bad sample, we do the next best thing. And we talk about how likely is it that this was a good sample? What's the likelihood that what I've done is actually meaningful, is actually representative? And that can feel a little underwhelming, because if we just do one study and we're like, well, there is a chance. Even if it's a small chance, there's a chance that everything is just completely wrong. That doesn't feel great. But in reality, we can repeat studies and we can repeat trials and experiments. And if we have a really, really high confidence, the likelihood that all of them were wrong and misleading, especially in the same way, is tremendously unlikely. So it's really important to state how confident we are of our numbers. And we do that with something called confidence intervals, which is just going to be a range of values and how likely we are that the real number, the population value, is in that range. Okay. So to do that, we need a couple things. First, we have to look at the margin of error. So if we're creating a range, like we've calculated a mean for a sample, we want to get a range of probable values for that sample. We need to know what to add and subtract from our mean to create that range. And that's the margin of error. So that's just the distance from the reported value that, like the limits, the furthest away from our observed value in our sample that the real value is likely to be. So the smaller the error margin, the more accurate the measurement, And to calculate it, the margin of error, E, is equal to Z, which is the Z value, times the square root of P, which is the probability from our confidence interval. Sorry, not the probability of our confidence interval, the probability that we've observed of the event happening the way it did. So if we did 20 trials and 5 of them are what we are counting successes, then that would be 5 out of 20 or a quarter. 1 minus P is just the complement of that probability, and N is the number of trials, the size of our sample. So we can use that formula to calculate the margin of error. The second thing we need for our confidence interval is our confidence level. So this will affect the Z-score in our formula. So it depends on how confident we want to say we are. So when you're doing statistical studies, how confident you want to be can vary. Certain things that are not the most critical, a confidence level of 90% could be plenty. For something really, really important, you might want a confidence level as high as 99%. And then these Z-scores, we could look these up on the Z-chart. Basically, where they come from is if we were to do our normal distribution, we want to catch, say, 99% in there. So that means that each tail would be 0.5%. And then we'd have to look up those numbers on our Z chart, subtract them, see what we get to give us actually 99%, and that's where you get these Z values from. We're not going to bother doing all that ourselves, but that's where they come from. So the question will always tell you what confidence level it should be, and then you can just take the Z-score from this table and work on that. And now that we have it, we can use the confidence level to determine our Z-score. The Z-score goes into calculate our margin of error, and then the margin of error is used to create what we call our confidence interval. So that would be our value that we're studying minus the margin of error for the lower bound and plus the margin of error for the upper bound. And quite often they then refer this to the confidence level. So for example, 95%, it might say this, we believe the true range of the population falls between this and this, 19 times out of 20, for example, for 95%, because 95% is 19 out of 20. Okay, so I think I've prattled on enough. Let's use this in a couple examples. So we have a study done in 2009 studying fish in Lavalle Lake. So in 2009, they caught 911 fish, 234 were trout. In the year 2012, they repeated the study. They caught 689 fish, of which 141 were lake trout. So what percentage of the fish, that's worded badly too, determine the percentage of fish that were lake trout, basically, each year. So in 2009, we had 234 trout out of 911 fish, which gave us 0.25686, or roughly 26%. We'll just do to the nearest percent for this one. And then in 2012, we caught 141 lake trout out of 689 fish. It gives us a value of 0.205. Well, I should not round twice. That would be a very bad habit indeed. 20464, which is let's say 20% to the nearest percent. Okay, so what's the margin of error if we have a 95% confidence level? So 95% confidence level, remember, means that Z is equal to 1.960 in our chart up here. 1.960 for 95%, which is the most common confidence interval that you'll work with. So let's calculate our margin of error. Let's break it up by year again. So in 2009, E would be equal to Z, 1.960, times the square root of our percent, which is 0.26, times our 1 minus percent, 1 minus 0.26, for 1 minus P, all divided by the size of our sample, which was 911 fish that we caught. When you calculate that, you will get plus or minus 0.028, or plus or minus 2.8%. And then for 2012, we do the exact same thing. E is equal to 1.960 times the square root of the probability, which is 0.2, times 1 minus the probability, all divided by the sample size, which was 689, gives us a margin of error plus or minus 0.030, or plus or minus 3.0%. So, what's our confidence interval? Well, for 2009, our confidence interval is going to be our 26% minus 2.8%, and the upper bound is going to be 26% plus 2.8%, for a confidence interval of 23.2% to 28.8%. And in 2012, we do the same thing. The confidence interval, let's give it a name. In this case was 20% minus 3% for the lower, 20% plus 3% for the upper bound, or 17% to 23%. So what does this mean? This means that 19 out of 20 studies we do, 95% of the time, which is 19 out of 20 studies, we successfully captured the mean, or the proportion of fish in these intervals. So 95% of the time we do this study, we will capture the true percentage of lake trout. So that's pretty confident, right? 95% of the time. We're 95% certain, in other words, that it's in that interval. It's not perfect, but it's pretty good. And that's a lot of what we do in statistics. So what can we conclude based on these numbers then? Well, if we look, the lowest bound in 2009 was 23.2, and the highest bound in 2012 is 23%. So we're pretty confident that the percentage of trout in this lake is decreasing. We don't know how much. It could just be that 0.2% change. Or it could be as much as from 28.8 to 17%, an 11.8% change. We don't know how much, and we can't misstate that in our conclusion. But we can say with 95% confidence that the percentage of fish in the lake that are lake trout is decreasing at least a little from 2009 to 2019. Awesome. Second example of this, we have the Montreal Expos. Montreal had a baseball team for a while. They moved to Washington. Wow, so many typos on this one. In 2005. A survey was done in Montreal several years later to see if the team should come back to Montreal. They surveyed 1,589 people, and 69% were in favor. So let's determine the margin of error and the confidence interval for the survey with a 99% confidence level. So a 99% confidence level means that our Z value will be 2.576 from that table up above. So we need to get our margin of error, which is equal to Z, 576, times the square root of the probability, so 0.69 were in favor, which means 0.31 were opposed, divided by the number of people surveyed, 1,589, giving us a margin of error of plus or minus 0.1115 or plus or minus 11.2%. Then we can use that to calculate the confidence interval. So our confidence interval is the 69% that were in favor minus 11.2%, and on the plus side 69% plus 11.2% for the upper limit, or 57.8% to 80.2%. So somewhere between 57.8 and 80.2% of those surveyed were in favor. And this is a pretty big range, right? We're talking almost 23%. But it makes sense because that's with a very, very high degree of confidence. So we are almost certain the true population value would be in there somewhere. So we can't claim that it's 80% that are in favor, but we can claim that we're certain that it's over half. We're absolutely certain it's over half. Within, where is it in there? We don't know, but it's definitely in there. So second survey, where's my mouse? Here we are. with a confidence level of 95%, found that 56% were in favor this time, with a margin of error of 5.2%. So, how many people were surveyed? Sorry about that. I got my notes mixed up on some values here. So, if you were calculating along, you would have noticed some errors. So, I'm just going to tidy this up real quick. So, according to my calculator, that is 0.023, or plus or minus 2.3%, 2.3, 2.3. There's a much smaller interval. All right. So 66.7% to 71.3%. Wow, that's a much more reasonable. So yeah, at least 2/3 of all people. That's a very reliable number, especially for a 99% confidence interval. But the reason you can get such a high number there is because we have such a huge sample, right? That's a very, very nice large sample. Sorry about that. Okay. So our second survey, for real this time, gave us a 95% confidence level that 56% were in favor, with a margin of error of 5.2%. So, how many people must have been surveyed? So we need to link together our confidence level. So 95% again gives us a Z value of 1.96. All right. And then we'll use our formula. E is equal to Z times the square root of P times 1 minus P over N. And it's algebra time to solve for N. So P was equal to 0.56. So 1 minus P is equal to 0.44. And we'll sub everything in. And our E value is 5.2. 0.052. So 0.052 is equal to 1.9. Let's tidy that up a little bit. 1.96 times the square root of 0.56 times 0.44 over n. So we'll divide both sides by 1.96, and we get 0.052 over 1.96 is equal to the square root of 0 point, no, I cannot write. 0.56 times 0.44 over n. We'll square both sides. So 0.052 over 1.96 squared is equal to 0.56 times 0.44 over n. So we're going to have to multiply both sides by n to get the n over here, and then divide both sides by that to get that over there and the n by itself. So n is going to be 0.56 times 0.44, all divided by 0.052 over 1.96, all squared. Don't round in the middle. If you calculate in pieces, keep lots of decimal places. And if we work all this out on the calculator, 0.56 times 0.44 divided by, in brackets, 0.052 divided by 1.96, close the brackets, all squared. I get 350.06 So therefore, approximately 350 people must have been surveyed. All right, there's a little bit more to this note, but this is already half an hour long. We'll deal with that when I get back. All right, so we'll call it there. There are still practice problems. These ones are for properties of the normal distribution, like 1 standard deviation away, 2 standard deviation away, 3 standard deviation away, the percents and all that. And then these are about confidence intervals. And we'll see you when I get back.